Hello friends, welcome to my class of physics. Now in this lecture series of damped vibration, today I am going to discuss the decay constant or relaxation time. Now this decay constant or relaxation time can be defined as the time at which the amplitude of an underdamped oscillation decays to 1 by e times of the initial amplitude, that is a0, and we can write it in this equation: a function of t equal to a0 e to the power minus bt. Now let's say at t equal to tr time the amplitude is atr, so it becomes a0 by e. Now if I put this in this equation, that will then it becomes a0 by e equal to a0 e to the power minus b tr. So from there we can reach to this expression of tr equal to 1 by b. Now you can see that if the b is increasing, if you have very high damping system, then this relaxation time will be less, right? If b is very small, then tr will be very large, right? So this is the concept of decay constant. Now it will be helpful, this expression will be helpful for you in many numerical problems. So please remember this form, that tr equal to 1 by b. Okay, now next we will discuss the logarithmic decrement, which is another important term in this damped vibration lecture. Okay, let's see. Now as you know that the amplitude decays is a0 e to the power minus bt, so it will be oscillating like this. As you know that in underdamped oscillation, that form is a0 e to the power minus bt sine root over omega square minus b square t plus phi. So that amplitude decays to a0 e to the power minus bt. So that's why you can see the tip of this sine wave is basically decreasing, right? Now if we consider at time t by 4, the amplitude is a1. Okay, so we can write a1 equal to a0 to the power minus b t by 4, right? And at time t plus t by 4, that is the after a full cycle, the amplitude will be a2, right? So now you see that what will be a2, form of a2, that will be a0 e to the power minus b t plus t by 4. Now in this way the amplitude decays to an. Okay, an if I tell, right? So now see how the expression will be. Now if we take the ratio of the consecutive amplitudes like a1 by a2, a2 by a3, a3 by a4, like that, so ultimately we will reach to an minus 1 by an, and you can see that the value is equal for each cases, that is e to the power bt. So we can tell that the ratio of successive amplitudes remain same, right? And if you take the logarithmic of that value, it will give us the logarithmic decrement. Now what is the importance of the logarithmic decrement? Actually it tells how the system is decaying. If the logarithmic decrement is high, then we can tell that damping is high, right? Now the term which we are going to discuss is the quality factor. So we can define the quality factor by this way: the ratio of maximum restoring force by maximum resistive force. Okay, so restoring force form, you know, that is minus kx. Now the maximum restoring force will be minus ka, where a is the amplitude of the vibration. Now in underdamped case, the form, you know, a is a0 e to the power minus bt, right? So that we have to write here. So let me write that, then I will tell you what will be the form of the resistive force. Now the form of the resistive force, we know that minus beta v, right? The v is the velocity, so that is dx dt. Now to find out the maximum value of resistive force, we require the maximum value of dx dt, and beta you know is called damping factor. Now what will be the maximum value of dx dt? So for that we require the form of x. X is the solution for underdamped oscillation, and if you remember the form, that is the x equal to a0 e to the power minus bt sine root over omega square minus b square t plus phi, right? So we have to take the first order derivative of that, so that we will do now. So let's see. Now you can see the form of the dx dt. Now for underdamped case, we know that b less than omega, so here we consider b very less than omega. So the first term, here the first term we can neglect, because you know there is a b term, right? So only the second term survives here. So the form remains like dx dt equal to a0 e to the power minus bt, and that root over omega square minus b square, that is also we can approximate to omega, and it becomes a0 e to the power bt omega cos omega t plus phi. Now for maximum value of dx dt, we know that cos theta is maximum value is 1, so that we can consider here, and we can get this maximum value of dx dt, so that we will use now. So let's see. Now if we put the form of the maximum value of the resistive force and the maximum value of the restoring force, so we can get that q equal to k beta by omega. Now k you know is omega square m, and beta by m is 2b. So if we put that form there, so we will be getting that value omega by 2b. So this expression also is important for many numericals in damped vibration problems. Okay, so please remember this. Okay, thank you.